Okay, in this video I'm going to do lots of derivative examples, and if there's one thing that you come out of Calculus 1 needing to be able to do, it's you need to be able to take a derivative. So in this video I'm going to talk about the product, quotient, and chain rule. I'm not going to do logarithmic differentiation. The derivatives I'll be using will involve power functions, polynomials, trig functions, exponentials, and logarithmic functions. No inverse trig functions, no hyperbolic functions, and some of the others. I'm not going to do all of the algebra either. It's just going to be, let's do the derivative, and that'll be our starting point for this video. So, just a reminder on all the little formulas that we're going to use here. So x to the n is n x to the n minus 1. The derivative of a constant is 0. We have our trig functions, sine, cosine, tangent, cosecant, secant, and cotangent. The derivative of e to the x is e to the x. The derivative of a to the x is a to the x times the natural logarithm of a. I hope that's legible there. So a to the x times natural logarithm of a. The derivative of ln of x is 1 over x, and log base a of x is 1 over x, natural logarithm of a. And I've got 25 problems here. Here's a quick glance of them all. Obviously you can pause these if you want to take a look at them a little bit longer, but these are the problems I have. Tried to make just a little variety of all kinds of different things. And there's the last page. So let's just start taking these in order, and hopefully we can make some sense out of them. So, all right. So the very first one we had, we're going to take the derivative of x squared plus 3x plus 4. So kind of a very basic fundamental one here. And the rule says, okay, if you take the derivative of this, remember there's lots of different notations for the derivative. One of them just being the little prime. Whatever exponent's upstairs, it comes out front, and we take 1 away from the exponent. If you have a number times a variable to the first power, in essence the variable just kind of falls off, and you're left with the constant. And then the derivative of the constant 4 is simply equal to 0, so that would be our derivative, simply 2x plus 3. Number 2, we've got 5 times t to the negative 2/3. People don't like the negative fractional exponents, but don't be too worried. There's a rule that says if you have a constant times something with a variable, you can use the product rule, but what it reduces to is the constant just gets carried along, and we're going to do the same trick. So the negative 2/3 comes out front. We have to subtract 1 away. So we're subtracting 3/3, so that would give us to the negative 5/3. In this case, there's not a ton of simplification. Negative 10/3. You could put the t to the negative 5/3 back downstairs and make it t to the positive 5/3. So I said I wasn't going to do all the algebraic simplification. Some of the easy, quick stuff I will, but some of the longer stuff I probably will not here. So. Alright, the next one we had 3 to the x minus 1 over square root of x. The first thing I would do is rewrite this as 3 to the x minus 1 over x to the 1/2. Now you could start using the quotient rule immediately on this one, but something that's very important to remember is if you can do any sort of algebraic simplification before you take the derivative, that's usually the way to go. So notice I could break up this fraction, 3 to the x over x to the 1/2 minus 1 over x to the 1/2. And now we have like bases. I have x to the first on top. I have x to the 1/2 on the bottom. I can subtract my exponents. 1 minus 1/2 would be simply 3x to the 1/2. To take the derivative of the 1 over x to the 1/2 part, we'll move the x to the 1/2 upstairs and change the sign on its exponent. So notice we haven't done any derivative yet. All we're doing is just algebra, just rewriting it at this point, trying to put it in a good form. So now we'll take the derivative. So again, just like before, the constant comes along, the 1/2 comes out front, we take 1 away, so 1/2 minus 1 will be negative 1/2. So there's the first part. Here's my minus sign, there's my minus sign. Same thing, x to the negative 1/2. The negative 1/2 comes out front. We subtract 1 away, so we'll subtract 2 over 2 and get negative 3/2. And you can think about the 3 as being 3 over 1, so we'll have 3 over 2, x to the negative 1/2. Two negatives make a positive 1/2, x to the negative 3/2. And that would be your derivative. So you could certainly get common denominators, put your x's back downstairs, get common denominators, and rewrite things. But again, in this, let's just be focused on, I'm just interested in actually mechanically doing the derivative process. Alright, so let's look at number 4 here. Okay, so number 4 we had x plus 4 times the quantity x minus 4. Oh, my 4 got a little sloppy. Again, you could use the product rule on this one immediately, but what I would do is simply multiply this out first. So you have x times x, which is x squared. We'll get negative 4x, a positive 4x, and then a negative 16. So if we simplify that, that's just a difference of perfect squares. We'll have x squared minus 16. So now the derivative is very easy to take. The 2 comes out front. We take 1 away from the exponent. The derivative of negative 16 is just 0. So that's going to be our derivative. So obviously you could have again used the product rule and simplify it down, but kind of illustrating again that it's much easier simply to just simplify first. So number 5 we have square root of x minus 1 over square root of x plus 1. Maybe there's some clear simplification of doing this. I don't really see it. So I think in this case we're just going to use the quotient rule. So x to the 1/2 minus 1 over x to the 1/2 plus 1. And remember what the quotient rule says. It says if you have a fraction, so something divided by something, we want the derivative of that. The formula says we get the bottom thing times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So no derivative in the bottom, just square what originally was there. Alright, so we'll use this little formula here. See if I can squeeze it in here. So it says whatever's on the bottom, we get that. So x to the 1/2 plus 1. We have to take the derivative of the numerator. So x to the 1/2, the 1/2 will come out front. We'll take 1 away. I'm totally going to run out of room here. So let's make it happen. So we have x to the 1/2 plus 1, 1/2 x to the negative 1/2. Always put a minus sign in the middle. Again, we may have to change it here in a second, but we always just use a minus sign initially. Then it says whatever's on top, write it. So x to the 1/2 minus 1, and then we take the derivative of the bottom. Again, x to the 1/2 plus 1 will give us 1/2, x to the negative 1/2. Again, the derivative of the constant is simply going to be 0. And then we take the denominator, x to the 1/2 plus 1, and we square it. Okay, so again, I'm not going to simplify this out, but I think this is, it's certainly a moderately tedious part. I would just distribute the 1/2 x to the negative 1/2, to the x to the 1/2 plus 1. I would do the same thing on the right side, and then try to factor it. So it's going to turn into a bit of a tedious algebra problem, but there is the derivative at least. Alright, so our next one here, number 6, we had y equals 2x minus square root of x times x, all divided by x squared. So again, this is something you could use the product rule and the quotient rule, but let's just simplify first. So we have 2x, again, square root of x, this is really x to the 1/2. So if we multiply that by x to the first, we'll have x to the 3/2 power over x squared. And again, we can simplify that. We can make that 2x over x squared, which will give us 2 over x. We'll have x to the 3 halves over x squared. So I'm going to do two steps at once here. 2 over x, I'm simply going to write that as 2x to the negative 1. X to the 3 halves over x squared. So 3 halves minus 2, you can think about the 2 as being 4 over 2. So you may have to write this down to the side if you're a little rusty with your fractions. 3 halves minus 2 will give us to the negative 1 half. So now if we take the derivative of that stuff, the negative 1 will come out front. So we'll get negative 1 times 2, or negative 2, x to the negative second. The negative 1 half and the negative 1 will multiply to make positive 1 half. And then we'll subtract 1 away and get to the negative 3 halves power. Alright, let's keep on going here. Let's see, number 7, we had y equals sine of x times square root of x. I'm going to go ahead and write that as x to the 1 half power. So in this case, we're going to have to use the product rule. I think we went ahead and jumped to the quotient rule a second ago. And remember, the product rule says if you have two things, f times g, it says if we take the derivative of that stuff, it says you take the derivative of one part, leave the other one alone, and then we just kind of switch them out. Okay? So because of this plus in the product rule, it doesn't matter the order we do it in. So to me, that's kind of one good thing. I don't have to worry about that. Remember, with the quotient rule, you definitely have to get the order correct in the numerator because of the minus sign. Alright, so it says the derivative of this. If we take the derivative of the first one, the derivative of sine is just cosine. We can leave the x to the 1 half alone. So you can think about this as being the f prime, this is being the g function, and now we leave the sine x alone, and then the derivative of x to the 1 half will just be 1 half x to the negative 1 half power. Okay, and we've got our derivative. So number 8, we had y equals sine x times cosine x. We're just going to use the product rule again. The derivative of sine will be cosine x. So we also have the original cosine x hanging out. Plus, now I'll leave the sine x alone. The derivative of cosine x is negative sine x. So we'll simply be left with cosine x times cosine x, which we can write as cosine squared x. A positive and a negative is a negative. Sine squared x, and we could leave it there. Remember, there's also a trig identity for this, cosine squared minus sine squared. We could even rewrite that as cosine of 2x. There's a trig identity that says that these two quantities are in fact equal, so you don't have to, but just a little thing to point out. For example, if they wanted us to take a second derivative, to me, we could take the derivative of this side using the chain rule. But it would be much easier to take the derivative of the right side using the chain rule. So again, this idea of simplifying before you take derivatives. But again, in this case, we're just doing a single derivative, so I think either one of these would be acceptable. Number 9, we had sine of cosine x. Now notice this is not the product rule. This is just the chain rule. If we had sine of x times cosine of x, this would be the product rule. But here we just have sine of cosine, so it's not the product rule in this case, but the chain rule. Okay, so if we take the derivative, to me, I always think about it as being the outside-inside rule. If you take the derivative of sine, you get cosine. We leave the inside alone. And then by the chain rule, we take the derivative of the inside. So the derivative of cosine is, again, negative sine x. So if you wanted to, you could pull the negative out front. I guess let's do that. I'm even going to write it as negative sine x, and then cosine of cosine x. And we've got our derivative. Alright, we're having fun. You could do this all day. You could. I think I would get bored. But alright, so number 10 here, we have y equals secant we had the square root. I'm going to go ahead and write that as 1 plus x squared to the 1/2 power. And I'm going to stick a set of brackets on there for myself just to kind of help myself visually break it up. So if I take the derivative, again, remember the derivative of secant x is secant x tangent x. So in this case, we're going to have to use the chain rule. So we'll get secant of the inside stuff, so 1 plus x squared to the 1/2, secant and tangent of the inside stuff, 1 plus x squared to the 1/2. But now by the chain rule, we have to take the derivative of the inside. But this again, I think, is where it's a little tricky, because we're actually going to have to use the chain rule a couple times. So to me, we've kind of done the secant portion of the derivative at this point. So now I just think if I had to take the derivative of this function, what would happen? Well, the 1/2 would come out front. I would leave the inside alone, subtract 1 from the exponent, so I'd get negative 1/2. And then again, kind of the same thing. I keep sort of moving inside. So now I've taken the derivative, I've accounted for the 1/2 portion of it. So now if I move inside yet again, the derivative of 1 plus x squared is simply 2x. And that would be the derivative of my function now. Okay, so obviously we could clean this up a little bit. The 1/2 and the 2 cancel. You could put the 1 plus x squared back in the denominator, but again, that is not my intent, so we'll just leave it there for the moment. Alright, so number 11, we had y equals tangent squared of sine of theta cubed. Again, I'm going to rewrite this. This tangent squared, it means the same thing as tangent of sine of theta cubed. All of that is what's being squared. Okay, so almost all the time I like to rewrite these things just to really see where the kind of what's on the outside and what's on the inside. It's easy for me to kind of make a mistake when I do the chain rule, I think. Okay, so if I take the derivative, going to be a long one here, so the 2 comes out front. We leave the inside alone. So I'm just going to rewrite it all without really even thinking too much about it. Take 1 away from the exponent, so now we have to the first power. So to me, now I've accounted again. I took the derivative of the exponent part. The derivative of tangent is secant squared, but again, we leave the inside alone. Sine of theta cubed. Okay, so at this point now I think, well, I've done the derivative of the tangent part. That's where the secant squared came from. So I move inside. The derivative of sine is cosine. Again, I leave the inside alone. And now the last thing I'm left with on the inside is the theta cubed. So the derivative of that is just 3 theta squared. And now we have, again, our derivative. Alright, let's see, number 12. And this one we had y equals x times sine of 3 over x. But again, 3 over x, I'm going to write that as 3x to the negative first. So on this one, we're going to have to use the product rule. I have one thing, I have something else. I'm also going to have to use the chain rule when I take the derivative of the sine portion. Okay, so the product rule, if I take the derivative of 1x, I'll get 1, and then we can leave the sine portion alone. We stick our plus in between. Now I'm going to leave the x alone. And if we take the derivative of the sine, 3x to the negative 1, the derivative of sine is cosine. Again, we leave the inside alone. And then the derivative of 3x to the negative 1, we'll get negative 3. And be careful, we have to subtract 1 from our exponent, so we'll get to the negative second power. And now we have our derivative. Alright, so I guess we're sort of almost halfway there. Alright, number 13 here. So here we had y equals x cubed plus 4 squared. all divided by x squared plus 1 to the 4th power. So here we're going to have to use both the quotient rule and the chain rule when we take the derivative. So the quotient rule, again, it says you get whatever's in the denominator times the derivative of what's in the numerator. So we're going to have to use the chain rule when we take the derivative of the top. So the 2 comes out front, we leave the inside alone, we take 1 away from the exponent, and then whatever's on the inside, we have to take the derivative of that, so we'll get 3x squared, minus, so now we leave the top part alone, and the same thing, we'll just take the derivative of the bottom. So the 4 would come out front, we would leave the inside alone, and then we would take the derivative of the inside, which would be 2x. If you take the denominator, x squared plus 1 to the 4th, and you square it, remember you multiply, so we would get x squared plus 1 to the 8th. And certainly this would be a problem that you could very easily simplify into something much nicer. So again, I'm not going to do that. I just want to talk about derivatives. But you know, if you're, for example, practicing for a test or trying to review, I would certainly maybe take it, try to simplify this down to make sure you can do the algebra. Okay, number 14. Okay, so in 14 we had y equals, so some logarithms here, ln of x plus x cubed. Nothing crazy here. One thing to be aware of with logarithms, though, is if there's any sort of algebra, remember there's all these properties, and we'll see some in a minute. The products turns into addition, division turns into subtraction, exponents can come out front. A lot of times the trick with logarithms is to simplify them, but here everything's pretty much already simplified, so we'll just take the derivative. So the derivative of ln of x is just 1 over x. The derivative of x cubed is simply 3x squared, and now we have our 15 was x squared times e to the x. So again, here we're just going to have to use the product rule. So the derivative of x squared is 2x. We can leave the e to the x alone, plus now we'll leave the x squared alone, and the derivative of e to the x is just e to the x. So again, we have our derivative. Alright, number 16 here. We've got y equals e to the t times cosine of 2t. On this one, we're going to have to use the chain rule. And again, kind of the basic formula. It says if you have e, so it says if you have e to something, some function f of x, it says the derivative of that, it says it just repeats itself. You get e to the f of x. But then by the chain rule, we have to take the derivative of the exponent. So in this case, the derivative will get, well, it'll just repeat e to the t cosine of 2t, but then we have to take the derivative, t times cosine of 2t. We have to take the derivative of all that, which means we're going to have to use the product rule and the chain rule as well when we did this. So we have our e to the t cosine of 2t, the derivative, okay, so now I'm focused on the inside, I'm using the product rule. So the derivative of 1t would just be 1. We'll leave the cosine of 2t alone. Product rule has a plus, we'll leave the t alone. The derivative of cosine is negative sine. Again, leave the inside alone. And then the derivative of the 2t part will simply give us a times 2. And I think I've got enough parentheses. Nope, I think I need one more. And there's our derivative. Again, you could rewrite this term as negative 2t sine 2t, but I don't see a ton of other simplification to do, at least in this example. So here's another one, 17. We'll have to use the chain rule. So cosine of e to the pi x, we'll have to use the chain rule twice. The derivative of cosine is negative sine. Leave the inside alone. And then we take the derivative of e to the pi x, again using this formula. It says e to the pi x will just give us e to the pi x. We have to take the derivative of pi times x, and that'll just give us times pi. Alright, number 18, getting close. So y equals, we had the square root of 1 plus 2e to the 3x, so I'm going to write it as 1 plus 2e to the 3x all to the 1/2 power. So the derivative here, the 1/2 will come out front. We leave the inside alone. We subtract 1 away from the exponent, so to the negative 1/2. And then, just like before, we have to take the derivative of the inside. The derivative of 1 is simply 0. 2 comes along. The derivative of e to the 3x will be e to the 3x. But then we have to multiply by the derivative of the exponent, which will just give us an extra 3. And again, you could clean this up a little bit. Certainly the 1/2 and the 2 would cancel out. You could stick this term in the denominator of the fraction if you wanted to. Okay, let's see. That was 18. Number 19. So in number 19, we had y equals 5 raised to the negative 1 over x. And again, I'm going to write that as 5 raised to the negative x to the negative first, just by bringing my 1 over x to the, the numerator and changing his sign. So just like before, the derivative of a to the f of x, it's going to be very analogous to the other formula we saw. That's going to give us, it's going to repeat a to the f of x. We have to tack on this natural logarithm of the base, but then again we have to take the derivative using the chain rule, so f prime of x. Okay, so the derivative in this case, I've got a number to some variable stuff. It's just going to repeat. And again, if you want to rewrite the original part as just 5 to the negative 1 over x, I say go for it. So now we have to take the derivative. Okay, so I wrote my natural logarithm first, so let me go ahead and stick my natural logarithm of my base in there, times 5. And then we have to multiply by the derivative of the exponent. So negative 1 would come out front, multiply by the negative 1, that would make a positive 1. So we'd have positive 1x, subtract 1 from the exponent, so we would get to the negative 2nd power. And that would be our derivative in this case. Let's see, 20. Okay, here we have the natural logarithm of x to the 4th times sine squared of x. Okay, the formula for natural logarithm, again in general, if you have the natural logarithm of some stuff, the derivative of that, it says you get 1 over that stuff times the derivative of whatever's on the inside. Okay, so I could go ahead and start doing that straight away, but when I take the derivative of the inside, I'm going to have to use the product rule and the chain rule. But remember, there's a property of logarithms that says you can break these up. So we can write this as x to the 4th plus the natural logarithm, and I'm going to rewrite my sine squared as sine of x quantity squared. And remember, there's also a property that says exponents can come out as coefficients. So we can write this as 4 times ln of x plus 2 times the natural logarithm of sine x. And to me, this is now in a much better form for when I take the derivative. Okay, so the constant 4 comes along. The derivative of ln of x is simply 1 over x. The 2 comes along. The derivative of ln of sine x, it says, well, you get 1 over sine x, but then we have to multiply by the derivative of the inside, which will simply give us a cosine x. So you could write this as 4 over x. Remember, cosine over sine is cotangent, so we could make it 4 over x plus 2 cotangent x if you wanted to. Again, my advice, when you're doing homework, or again, if you're studying for a test, take the time now to kind of practice the algebra. I think in most classes, Sometimes they'll be, lenient and say don't worry about it, but in general, eventually you have to be able to simplify, so certainly try to practice that. Number 21, same idea. We have natural logarithm of the square root 5x minus 1 over 2x plus 3. I'm going to break this up before I take the derivative. So ln of 5x minus 1 over 2x plus 3. This is all to the 1/2 power. Well, I can pull the 1/2 out front and then have the natural logarithm of the 5x minus 1 over 2x plus 3 hanging out. But now we can break up the fraction as subtraction. So the natural logarithm of 5x minus 1 minus the natural logarithm of 2x plus 3. And now we can simply take the derivative. So the constant 1/2 just comes along. Since there's a minus in between here, we just do them a piece at a time. So the derivative of ln of 5x minus 1 will get 1 over the stuff, which is 5x minus 1. We have to do the chain rule. The derivative of the inside will be times 5. Again, you can certainly stick this in the numerator. That's where it'll end up going. And then the next portion will get 1 over 2x plus 3. And then the derivative of the inside will just be a times 2. I put the 2 in parentheses and not the 5. I don't know why, for no particular reason. It doesn't really matter. So at that point, you've got your derivative. 22, let's see, so I think this one was a little not too tricky. T cubed minus 3t. Again, just trying to illustrate here the difference between a polynomial and an exponential function. So the derivative of t to the third, the 3 comes out front, we take 1 away from the exponent. But the derivative of 3 to the t, it's an exponential, so it just repeats, and then we have to tack on the natural logarithm of the base, which in this case will be 3. Let's see, I think, well, let's just go to another piece here. Alright, 3 to go. So number 23 is the natural logarithm of secant x plus tangent x. The derivative of that, again, it says you just get 1 over the stuff. So secant x plus tangent x. And then it says we have to multiply by the derivative of the inside. So the derivative of secant x is secant x times tangent x. And then we have the derivative of tangent x, which is secant squared x. And again, now we have our derivative. I think you could definitely do some algebraic simplification on this. Notice you could factor a secant from the numerator. What would we have left? We'd have tangent plus secant, which would cancel out. So unless I'm crazy, I believe all this is going to just reduce to secant x. So you can check that and make sure. Let's see, number 24. We have log base 10 of 2x over x minus 1. So I'm going to do the same thing. First thing I'm going to do is just break it up. Log base 10 of 2x minus log base 10 of x minus 1. We could even break up this first term again because there's multiplication. We could turn it into addition, but I don't think that's quite necessary here. So the derivative, it says, if you have a logarithm, it says you get 1 over the stuff. You have to tack on the natural logarithm of the base, so we'll end up with a natural logarithm of 10 in the denominator. And then by the chain rule, we just take the derivative of the inside, which will be times 2. Do the same thing for the next part, the x minus 1, that goes downstairs. The derivative, we'll have to tack on the natural logarithm of the base, which is 10. And then the derivative of the inside would just be times 1. So again, you've got your derivative. Alright, the grand finale. Number 25. We had y equals ln of x over x squared. So again, nothing too crazy here, just kind of a basic quotient rule one. So the derivative, it says we get the denominator times the derivative of the top, the numerator, so we'll just get 1 over x, minus the numerator, the derivative of the denominator would just be 2x, and then it says take the denominator and square it, which will be x to the 4th, and again you have your derivative. So certainly the x squared times 1 over x can just reduce to x to the 1st. You could probably factor and definitely cancel out a little more from there. But again, I'm just trying to emphasize the basic derivative procedures. So, alright, I hope these bunch of derivative examples give you a nice little summary. Certainly it's not everything. You know, you could do a million derivatives and still want to see a million more. So, but I hope this is a good little cross-section, maybe a good refresher for those of you who have been out for a little while. As always, feel free to post comments or questions.